All right, looking at 2.5 today. We're starting with 2.5, transformational functions. Now, I don't sit in 2.5 that long as far as lecture is concerned because all it is based on graphing. You have six basic functions or six parent functions. Excuse me. So the first one is y equal to x. That's just your linear equation, gives you a straight line. The second one, x squared, gives you that parabola. Then we have our cubic equation, square root of x, cube root of x, and the absolute value of x. So those are the six basic functions that they mention in this section. All right. From there, notice I put here the summary of your transformations for your function is going to be on page 291. All right. Let me know if I'm scrolling up too fast because I want to get to that bottom. So basically what happens in this section is that, if you need to use a graphing tool that will be in your best interest, make things easier for you to use a graphing tool. Once again, I'm not asking you to purchase a graphing calculator if you do not already have one. All you got to do is Google graphing tools or free graphing tools, graphing calculator in Google, and they will give you a bunch of free ones that you can type in the function and figure out what the graph is. So what's going to happen is in that summary, they focus on what happens. You notice if our parent function is x squared, if I put plus one inside of the square or plus one outside of the square, how does that shift my function? If I put minus one inside of the square or minus one outside of the square, how does that shift my function? So I could write down all of the transformations, or to me, the best way to do it is that you guys would go to your summary page of all of your transformations and look at and experience how it does it for itself. So in my math lab, for the most part, the problems, they'll have A, B, C, or D with these graphs and say what graph matches this function. And so if it was something like this, and we're trying to figure out what happens in these cases, the difference between the four is that your graph is going to shift up one, down one, left one, or right one, depending on which one of these transformations have occurred. So try it out, see if you have any issues with it, see if you have any issues with matching up your functions to the proper graphs, and then most definitely feel free to ask. But that's graphing. At this point, you guys should be pros at graphing. Um, so I'm not forcing you to graph anything by hand. It's just more so check out a graphing tool, see how these graphs translate and shift up, down, left, or right, and go from there. So questions on that before we go to 2.6. All right. 2.6, combination of functions and composite functions. All right. So first exercise they will probably ask you in this section is to find the domain. So you're looking for all the values that can be used for x, or in other words, all the values that can be plugged into the equation for x. So to find the values that can be used, you look for the values that cannot be used. All right, so we'll talk about what that means in a second. All right, so first exercise, find the domain of each. First one we have is x squared minus 7x. So whenever you're looking at your function, you want to ask yourself, is there a pre-existing condition in that type of function that will allow me to find values that won't work for it? When you look at x squared minus 7x, that's a parabola, it's a quadratic equation. And you're supposed to ask yourself, whenever you're looking at these functions, is there a value that can be plugged in for x that will make the equation undefined? Or is there a value that I cannot use? So when I look at these functions and I'm talking about a pre-existing condition, you'll see better when we look at the next example, what I mean by that. But when I look at this x squared minus 7x, there's nothing I can plug in for x that will make it undefined. There's not a value I can plug in for x that will not produce another value. So if I plug in 0, I will get a number out. If I plug in positive 1, I will get another number out. If I plug in negative 1, I will get a number out. So there's not a value I can plug in for x that will make this undefined or will not produce a number. So my domain would be negative infinity to positive infinity. Once again, when we look at the next one, you'll see what I mean by a value that I cannot use. But in this case, there's not something that I can plug in to the equation that cannot be used. All right, questions, any questions? All right, next one. G of x is equal to 2 over x over minus 5, x minus 5. So once again, can I make this equation undefined? In other words, in this case, a fraction. Can I make this fraction undefined? And so I use fraction loosely here. Another word or another term for fraction is rational expression. So this is a rational expression. So when is a rational expression or fraction undefined? Fractions are undefined when the denominator is 0. So that's why I was talking about a pre-existing condition. When I look at a rational expression, they are going to be undefined when the denominator is 0. So if ever I have a rational expression, I will set the denominator equal to 0 and then solve. Okay, so x minus 5 equal to 0. Solve for that, you have x equal to 5. And so be careful, this is not your solution. You see over here in the green, this is the value that cannot be used. It's the value that cannot be used. So that means my domain is everything else. I cannot use the 5, but I can use everything else. So notice I go from negative infinity to positive 5. I use parentheses on that 5 because that means I can get as close to 5 as I want, but I can't use 5. Then I go 5 to infinity. So I can use everything after the 5. All right, scrolling up. All right, next one. H of x is equal to 3x plus 2 over x squared minus 2x minus 3. So once again, we have a rational expression. We'll set the denominator equal to 0 and solve. X squared minus 2x minus 3 equal to 0. I decided to factor. So x minus 3, x plus 1. Get x equal to 3 and x equal to negative 1. Once again, these are values that we cannot use. These are not solutions. These are the values that we cannot use. 3 and negative 1.
You can't use them because why again?
These are values that make our denominator 0. Remember, we took the denominator, set it equal to 0. So when I plug in 3 into this equation, I get 0 in my denominator. When I plug in negative 1 into this equation, I will get 0 in my denominator. But remember, 0 in your denominator is undefined, so that's why we cannot use these. So we use everything except for the 3 and negative 1. And if you're talking about according to your number line, you will go from negative infinity to negative 1, negative 1 to 3, and then 3 to positive infinity.
Okay, I got a question.
Mm-hmm.
So you say you can't use them, but how come you use them in the answers?
Well, technically we aren't because of this parentheses right here. So what that parentheses says that you can get as close to negative 1 as you want, but you cannot use it. So it's just allowing us to get even decimal wise as close to negative 1 as I want, as close to 3 as I want. So I can use 3.1, I can use 3.01, I can use 3.000001, but I cannot use 3. So that's what that parentheses does for us. All right, make sure we get good questions. Make sure we're straight on what we're doing, why we're doing, symbolism, all that. All right. Everybody good. So basically these numbers help us to set up the intervals that we can use, intervals for our domain. And once again, emphasizing the parentheses, make sure you use parentheses here, because if you use bracket, it will be wrong, because using the bracket over the negative 1 means that you can use the negative 1, and you will be using the negative 1. Parentheses says that you're not using them. All right, one more like this. Here we have the function square root of 3x plus 12. So once again, we're asking ourselves, when or can I make this expression undefined, or when is a radical undefined? So when we talk about this radical in particular, it's the square root. You cannot take the square root of a negative number. Remember, we already talked about whenever you take the square root of a negative, those numbers will be imaginary. The result will be imaginary, taking the square root of a negative number. So we cannot take the square root of a negative number. So then we want to say to ourselves, well, when is the radicand greater than or equal to 0? And the radicand is what's under the radical. So 3x plus 12 is the radicand. So whenever you have the square root of something, you're going to take the radicand and set it greater than or equal to 0. So in this case, we're talking about or equal to, because you can take the square root of 0. No, 0 times 0 is 0. So you can take the square root of 0. So 3x plus 12 is greater than or equal to 0. Remember, the greater than are the positive values. Subtract 12, divide by 3. X is greater than or equal to -4. And so to write our domain, in interval rotation, that'd be -4 to positive infinity. And notice I use bracket this time because we're talking about or equal to. We can use that -4 because it's okay for it to be equal to 0. Before, it was not okay for my denominator to be equal to 0. Here, it is okay for what's under the radical to be equal to 0 because you can take the square root of 0. Square root of 0 is 0. So that's fine.
So we use the bracket when we're talking about greater than or less than, but if there's an equal sign, we do not use the bracket at all.
No. We use the bracket when you're talking about or equal, when you're talking about equal to. Now, it's all about, you got to remember what we're doing. It's more than just the symbol that you see. It's the statement that you're making. Okay. So here we want to know when is my radicand greater than or equal to 0? That's what we were solving right here, because it is okay for what's under the radical to be equal to 0 because the square root of 0 is 0. So that's why we can use the 4. Now, when we go back up here, we want to know when was my denominator equal to 0, because when it's equal to 0, anything over 0 is undefined.
Undefined, yeah.
Right. So now when these values are plugged in, that's when my denominator is equal to 0. So that means those are the values that I cannot use.
Not use.
Yeah. So it's more than just, okay, because I have this equal sign right here, I use parentheses.
Oh, I see that up there. We're talking about when is it not equal to 0, or when is it equal to 0. And here we're talking when it's greater than or equal to 0. So it's the difference is the greater than part down here.
Well, let me say this. The difference is, why are you trying to find these values? So when I go here and I say, I want to know when is it equal to 0, I want to know when is my denominator equal to 0, because when it's equal to 0, it's a problem, right?
Yeah, so we can't use it.
So we can't use it. Okay. Now, when I go here and say, when is this equal to 0, it's not a problem because the square root of 0 is
0.
Right. So that's the difference. Here, having 0 in my having 0 under my radical is not a problem. So that's why I can include it. That's why I can use it.
I understand. I get it.
But being 0, and I'll finish it off just in case somebody else didn't get it. Having 0 in the previous example was a problem. That's why I could not use those values. All right. All right. Good question. Good question. Everybody good copying before we go to the next one? All right. Now we're looking at the algebra of functions. They just give us shorthand ways of telling us what to do with our functions, whether it be adding, subtracting, multiplying, or dividing them. F plus g of x is f plus x, f of x plus g of x. Same thing with subtraction, multiplication, and division. No, when you go back to the last one, someone asked, does that mean you cannot use the 4? No, we can use the 4, because when I plug in 4 into that function, what was 3x? I look at 3x plus 12. When I plug that in, that's 3 times -4 plus 12. Square root of -12 plus 12. That gives me the square root of 0, and the square root of 0 is still 0. So having 0 under my radical is okay because I can take the square root of 0. I just can't take the square root of a negative value. So that's why we use the bracket on this 4 instead of parentheses, because I can use that -4. All right, I hope that helped. I hope that answered your question. All right. right. All right, so here we have f of x is equal to 2x minus 1. G of x is equal to x squared plus x minus 2. And they ask us to find each. So they defined our functions here. And we have to apply the algebra accordingly. First one, f plus g of x. All they want us to do is add f of x and g of x together. So all we will be doing is combining the like terms. I want to do that. So combine your like terms. X squared can't be added to anything. But then you have 2x and 1x, which would be 3x. And then negative 1 and negative 2, which would be negative 3. All right, next one, f minus g of x. Subtract your functions. Don't forget to distribute the negative to each term that follows. And then combine your like terms. So that'll be negative x squared. 2x minus x is x. And then negative 1 plus 2 is positive 1. Next one, f times g of x. So you're going to multiply the functions. So we have 2x minus 1, x squared plus x minus 2. You multiply them together. 2x times x squared is 2x cubed. 2x times x is 2x squared. 2x times negative 2 is negative 4x. You multiply negative 1 to each one of those terms, give you negative x squared minus x plus 2. Combining your like terms, negative x squared and, well, yeah, negative x squared and positive 2x squared. Give you x squared, and negative 4x minus 4x will give you negative 5x. That would be your most simplified expression. Last one like this. F over g of x. So you just place f of x over g of x. If you can simplify, they would expect you to do so. This one could not be simplified. So that would just be it. 2x minus 1 over x squared plus x minus 2. All right, questions on that? All right, so also it is possible that they could put a number in for the variable, you know, f over g of x. So if you were to put a 2 right there where x is, then all that means is that you will put a 2 wherever you see x in the function. And that's what I did right here. So it's 2 times 2 minus 1 over 2 squared plus 2 minus 2. We're going to simplify that. 2 times 2 is 4 minus 1, which is 3 on top. 2 squared plus 2 minus 2 give you 4 down bottom. All right. Questions? Any questions? All right, here we have the composition of functions. We have what we call Goff of x and fog of x. We're going to be looking at fog of x. You would take the g function, the one that appears second, and plug it into the one that appeared first. So you take g and plug it into f. For Goff of x, you take f and plug it into g. So be careful with these because they don't equal the same thing. Of course, if you're taking one function and plugging it into the other one and then reversing the process, they aren't going to give you the same thing. All right. So to give us our first, to give us our two functions, f of x being 3x minus 4, g of x is being x squared minus 2x plus 6. And they ask us to find fog of x. So that means I'm going to take this g function and plug it in where I see x. So that's what I did here. 3x squared minus 2x plus 6, plug in where I saw x. So it's 3 times x squared minus 2x plus 6 minus 4. So that 3 and that minus 4 is still a part of your equation. It's just that where x was, I put the expression x squared minus 2x plus 6. Once you've done your substitution, you can go ahead and distribute. So 3 times x squared minus 3 times, well, just 3 times x squared is 3x squared. 3 times 2 is at 6, and then 3 times 6 is at 18. And you still have minus 4 in the back. Combine your like terms, 18 minus 4 give you 14. All right, questions? All right, so now for Goff of x, we're reversing the process. So now I'm going to take f. I still have my eraser on. All right, so f, and then we're going to plug it in where we see x. So this time, I took 3x minus 4 and plug it in where I saw x. So that'd be 3x minus 4 squared minus 2 times 3x minus 4 plus 6. All right, so erase this out. Don't forget that 3x minus 4 squared is not 3x squared minus 4 squared. You know, you have to do your expansion properly. 3x minus 4 times 3x minus 4. So that's what this is over here. Just doing your binomial distribution. And that'll give you 9x squared minus 24x plus 6. Distribute the negative 2. That'll be negative 2x plus 8. And then at plus 6 is still in the back. Combine your like terms. 24x, negative 24x and negative 6x give you negative 30x. Then 16 plus 8 plus 6 gives you 30 in the back. All right. Questions before we look at C? All right, so if you have golf of 1, remember we looked at in the previous example, plugging in 2 for x. But in this case, let's say if we have 1 for x. If we look at the setup here, g of f of x, g of f of 1. So we just have a 1 that's in place of x in the process, but it's still the same process. So we can handle this one of two ways. I'll show you both ways. The first one, f of 1 is on the inside of here. So what I could do is find f of 1 first. So you plug 1 into the f function. 3 times 1 is 3. 3 minus 4 is negative 1. So now f of negative 1, plug that into the g function. So plug in negative 1, not f of negative 1. F of 1 is equal to negative 1. Plug negative 1 into g. And so negative 1 squared minus 2 times negative 1 plus 6. That simplifies to 9. So that's one way of doing that. All right. So the other way is that we already found that expression, and we can just plug in 1 into that expression. So that's the finished result of golf of x. Plug 1 into that expression. So that's 9 times 1 squared minus 30 times 1 plus 30. And you see that simplifies to 9. So either way, you'll get 9. It's just up to you which one or which way you want to go about doing it.
I got a question, Professor Tucker.
Yes, sir.
Like golf of 1, is this always, this question, this particular one, the golf of 1 or golf of 2, golf of 6, is it always going to be asked after we find the golf of x? Like you explained, we can use the golf of x here. So is it every time, is it going to be asked after the golf of x?
It does not necessarily have to be the case. I believe because they're doing the exercises and they want you guys to emphasize the process and all the stuff like that, it probably will, but it does not necessarily have to be the case. So if you were just talking about going from scratch, then this first method would probably be the easiest way to go if you were doing it from scratch. But if you already had this, like you just finished mentioning, if you already had this available to you because you already did the work, then that's when that method would be easiest to you. You can go ahead and just plug 1 into this finished product.
Professor Tucker,
Yes, sir.
I want to recite something back to make sure I got it.
Mm-hmm.
Golf, you taking that function, that first function, and plug it into the G function.
All right, now when you say golf, when you say first function, I just want to make sure we're saying the same thing, you know what I mean? So when I look at the way that this is worded, I would look at this as being the first function and this one being the second function, right? Because, reading it from left to right, G is first and then the F appears second. So what this says to me is that I'm going to take the second function and plug it into the first function.
Okay. Reading from left to right,
Mm-hmm.
take the first function, G, and plug in the second function.
Right. So you take that second function and plug it into, right, your first function.
Is you take the second function and plug it into the first function.
Mm-hmm.
All right. Thank you.
Not a problem. All right. Any other questions before we look at inverse functions? All right, so we'll look at 2.7 and then call it a wrap, and we'll talk about how we're going to move forward in the class. So 2.7 is inverse functions. So you let f and g be two functions such that f of g of x, in other words, when you take g and plug it into f, it reduces down to just x. And then when you take f and plug it into g, it reduces down to just x. So both of those have to occur if they're going to be inverses. You will get problems in which if you do one, it'll check off, but then when you do it the other way around, it doesn't. And that, they're trying to test to see if you're going to test both ways. So you do have to test both ways. Plug G into F, see if it reduces down to X, and then plug F into G, see if it reduces down to X. If that is the case, then that means G is the inverse of F. And then your notation here is F inverse of X. So you put that -1, superscript -1 as your exponent. All right. Oh, last point as far as general point of your inverses. The domain of F is the range of F inverse and vice versa. So your domain and your range flips for the inverse. So whatever's your domain will be your range for your inverse, and whatever your range will be your domain for your inverse. All right. So we want to show that the functions are inverses of each other. First thing I did was, we have f of x is equal to 3x plus 2, and then g of x is equal to x minus 2 over 3. I took x minus 3 and plugged it into x of my f function. So that's 3 times x minus 2 over 3 plus 2. Those 3's cancel, leaving you with x minus 2 plus 2. 2's cancel and leave you with just x. right, next one, we're going to do the same thing, but reverse the process. Take 3x plus 2, plug it in where I see x in the other function. So 3x plus 2 minus 2 over 3. So the parentheses there, nothing holding it there. I just put it there just to signify what was substituted in. So 2 minus 2 will cancel out, leave you with 3x over 3. 3's cancel, that'll leave you with x. So since both of those reduce down to x, that proves that they are inverses. Remember, like I said before, that has to happen for both ways. So g into f and then f into g both have to simplify to x. Once again, you will get problems wherein this one will work and this one will not, or vice versa. And they are seen if you're going to actually test both ways. All right, questions. All right. Okay. All right. So one-to-one functions. Hold on one second. I got stuff blowing away. Let me get somebody to get that. All right, sorry about that. Like I said, I got stuff blowing away on the front porch. All right, so one-to-one functions. If each element in the domain goes to exactly one element in the range and vice versa, then your function is one-to-one. So remember when we dealt with the domain, or not the domain, when we dealt with being a function before, each element in your domain went to exactly one element in the range, but it was okay for the range to go to multiple elements in your domain. So now if you're talking about one-to-one functions, each element in the domain goes to exactly one element in the range and vice versa. All right. The reason why this is important is because if the function is not one-to-one, then it does not have an inverse. Does not have an inverse. Thanks. All right, so our test. Remember we had the vertical line test. Now we have the horizontal line test. Same thing as the vertical line test, but this is for one-to-one functions. If a horizontal line crosses or touches a graph more than once, then it is not one-to-one. So just 3 examples of a function using the horizontal line test for a graph. So looking at that first one, that's y equal to x, our linear equation. That is one-to-one. The horizontal line only touches it once, no matter where you draw it. Second one, we have a quadratic, a parabola. So this is not one-to-one. So don't forget, though, it is still a function. It's just not a one-to-one function. Still a function, not one-to-one, though. And so if it's not one-to-one, that means that the quadratic equation would not have an inverse. And then the last one, the cubic equation, is one-to-one. No matter where you draw your horizontal line, you will always, it will only touch it once. So that means it is a one-to-one function. All right, questions. Almost finished for today. All right. So the last process for today, finding the inverse. First thing you want to do is check to see if the function is one-to-one. If not, then there is no inverse. So be careful there. You can do a whole bunch of work after or if you never check to see if it's one-to-one, you can do a whole bunch of work, get an equation, and that equation does not represent anything for you because you never checked to see if it was one-to-one. If it is not one-to-one, then there is no inverse and there's nothing for you to do after step one. You would just write, there is no inverse. All right, so always be careful with that. Your function has to be one-to-one in order for you to have an inverse. Once you've established that it is one-to-one, replace f of x with y, interchange xy for step 3, solve for y step 4, and then step 5 will replace y with f inverse of x. So that's just basically notation. All right. So let's try this out. So the first one we have f of x is equal to x cubed plus 1. So I just looked at the graph and used a horizontal line test, and that shows that it is one-to-one. Since it is one-to-one, that means we can continue on with our process. Step 1 is to take f of x and plug in y for it. Oh, hold on. Somebody said what's after the interchange? Solve for y. That's step 4, solve for y. All right. So I'll give everybody a second to catch up. So looking at step 1, we determined that our function was one-to-one. And that second step was to replace f of x with y. So that's what we did there. Third step, okay, somebody said something. Oh, well, you're going to see when we do the process. That'll be, I'll explain it. Yeah, that's what I'm going to get to. So I thought you just needed to see what was there. All right. So now the second step, well, we already did the first step with the horizontal line test. Second step, we already did it as well. We switched f of x with y, put y there. Now interchange x and y. So that just means you're going to put y where you see x, and then put x where you see y. So that's what we mean by interchange x and y. We flip their positions. So wherever you see x, put y. Wherever you see y, you see x. All right, everybody okay? Step 4, solve for y. So subtract the 1 from both sides. And then took the cube root of both sides to get the cube off of y. So you see we have the cube root of x minus 1, excuse me, is equal to y. Any questions? Any questions? So y is equal to the cube root of x minus 1. So your final step is to substitute the notation of f inverse of x for y. All right. Questions? Any questions? All right, I scroll up. All right. So next one, we're looking at f of x is equal to x squared plus 3x minus 5. Once again, the first step is to establish whether the function is one-to-one or not. All right, so that's a parabola. That means the function is not one-to-one. Therefore, there is no inverse. All right. So really, there's no more work to do after that as far as the inverse is concerned. Here, I was just emphasizing why there is no inverse when you're talking about how the inverse will be set up for your function. The actual horizontal line test turns to the vertical line test. And if that's the vertical line test, it establishes that your inverse would not be a function. So that's why to say if it's not one-to-one, then you don't have an inverse, because whatever is produced out of that will produce something that's not a function. All right. So once again, this extra stuff you don't necessarily have to lean on that much. The main thing is right here. If its function is not one-to-one, if it fails the horizontal line test, then there is no inverse. Questions on that one before we look at the last one for today? All right, so here we have f of x is equal to x plus 2 over x minus 3. So if you were to go to your graphing tool, check that one out, you would see that it would pass the horizontal line test. So that means it is a function. All right. So second step, take f of x, substitute it in for y, or substitute y in for f of x. Then we're going to interchange x and y. So y's are here, x is here, because at first the x's were over here and the y was right here. So we interchange x's and y's. All right. So notice we have y in our denominator. Your goal is to solve for y now, but we need to get that y out of the denominator. So I multiply both sides by y minus 3 to get that y minus 3 out of the denominator. That cancels out on the right. On the left, that gives us x times y minus 3 equal to y plus 2. All right, and then distribute X. That leaves us with this. It's XY minus 3X equal to Y plus 2. Now I have Y that's in two different places. I need to get it all of my terms with Y on one side, all of my terms without Y to the other side. So I subtracted XY from both sides and subtracted 2 from both sides. So that I'm looking at negative 3X minus 2 and then Y minus XY. So I still have Y in two different terms, but they're both on the same side. So now I can factor out Y from both terms. Divide both sides by 1 minus X. Then I have Y equal to negative 3X minus 2 over 1 minus X. And then final step, F inverse of X is plug in for Y. Questions? Any questions?
Just a quick question, Professor Tucker.
Mm-hmm.
It's about the step number 1,
Mm-hmm.
where you see this is a function, this is not a function.
Mm-hmm.
Can you tell me how, like, you do it on the graph, or we just use the graphing calculator for it?
To me, that would be the easiest way to use a graphing tool.
Mm-hmm.
And then you use the horizontal line test. Well, you throw a horizontal line through it. If it touches it more than once, then it's not one-to-one.
Mm-hmm.
And so that's the easiest way to establish one-to-one.
Mm-hmm. But I just is it okay if I want to know how you do it?
Oh, that's how I would do it.
But like, you didn't use a graphing calculator here, right?
I already knew what the graph looked like.
Okay.
Now this one, I would, to be sure, I would have threw that in the graphing calculator, because a lot of times we use rational expressions. Sometimes it can be a little funky.
Mm-hmm.
So that I would have went to, TI-81, or just type in graphing tool and then type this in Google. I mean, not in Google, I would Google graphing tool or graphing utility in Google, and then use that function in that and see what I got. So let's see. So, graphing calculator. I think decimals is a good one. And so parentheses x minus 2. Oh, I use parentheses x plus 3. And so that's what we're looking at. And so by looking at that, then I would have done my horizontal line test, recognizing that there's not a horizontal line that will cross this more than once, no matter where I draw it. So then I would have known it would have been one-to-one.
I see.
Yep,
Thank
yep.
you. Thank you so much.
Yeah, not a problem. But I most definitely wouldn't do it algebraically, because that would be kind of difficult if you already don't know what the graph looked like.
Okay.
Yep. Let's let's go back to the notes. All right. Anything else before I say anything else? Make sure we're good. Make sure we're okay. All right. So we're about to close out chapter 2. We only have one more section left. So if you do have questions next class, all we're going to do is 2.8. And so there should be room for questions, from other sections if you have them. Monday.
When is the next?
Hmm?
When is the next test?
I'm trying to get there. I'm saying.
Oh, okay.
No,
I
just
don't want
messing
to
with
take
you.
it.
You don't want to take it.
No.
That's funny. That's funny. So 2.8 we'll cover on Wednesday. So that will set us up for a review day on Monday. That means that will be an open class. I won't be covering anything new on that day. And then, so that gives you the weekend to go through your assignments, to bring whatever questions you want to bring on next Monday. Also, once again, at the end of next class, which will be Wednesday, there should be room to answer questions here, if you have them. And then, so on next class, we will establish how we're going to do this next test and when. So let me look at a few things. Same thing I told my last class. Let me look at a few things. So we'll talk about the next test on next class. So questions on how we're going to do things moving forward. I'm going to establish what we're going to do for the next test next class. Look at our last section in chapter 2 next class. Then I know we'll have a review day next Monday for you guys to ask whatever you want to ask. All right. Anybody before we close out today? Everybody good? Right straight. Okay. All right. So once again, try the stuff out. See if you get stuck. See if you have any issues. And I will see you guys on next class. You have a good day.
All right, Mr. Tuck, have a good one. Thank you.
All right. You do the same.
Appreciate it.
See you, Mr.
All right. Take care, sir.
I sent you an email.
When you send it.
Wait, can you hear me?
Yeah, I can hear you.
What? Yesterday maybe.
Oh, okay.
Saturday. It was just. I just want to know if you checked it or not yet.
If you sent it yesterday, I haven't gotten to my yesterday emails yet. So
Okay, then it
now
was probably yesterday.
You said it was probably yesterday?
Yeah.
Okay, yeah, give me a chance. I should be able to get to it. I'll probably get to it before the day is out.
Okay.
All right, cool.
Thank you. Have a nice day.
All right, no problem. You do the same.